Welcome back. Today we're talking about the intermediate value theorem. The intermediate value theorem is a very common sense theorem. So common sense that you might think we don't need to prove it, but it's a very important theorem in introductory analysis and we need to take it seriously. We're going to prove it using the definition of continuity and the completeness axiom for the real line. These are the two simplest tools that we will definitely need in order to solve it. So let's get to the statement of the theorem. If we have a function defined and continuous on a closed interval a, b, so that's represented here. And if we have furthermore, f of a is less than y is less than f of b. So we have this target value y, which we think of as a goal output value of the function. F of a is too small. F of a is less than y. And f of b is too large. F of b is greater than y. So we have this set up. Then there exists some x, which would be somewhere in here. There must be some value x between a and b, so that f of x is equal to y. In other words, so we can think of this as sort of a Goldilocks principle. If the function is sometimes too small and sometimes too large, and if the function is furthermore continuous between the region where it is too small and too large, then there must be some location here where the function value is just right. So that means f of x is going to be exactly equal to y. So this is common sense. If you draw this without lifting your pen, then you cannot cross through this line. I mean, you cannot get across this line without crossing through it, and where you cross through it, that will be the location of the value x, where f of x is equal to y. Very common sense principle, but that is, yes, it may be common sense, but we still have to prove it. So how are we going to do this? We're going to use the completeness axiom and the definition of continuity. Oh, there is one other case. That is, if these values are reversed, if f of a is too large and if f of b is too small, then again we get a value in between, which is just right. So we'll prove this statement, and then the proof of this statement is similar. You could do it in the same way, or you can deduce this statement from this. We'll get to that later. Two things you need to remember in order to understand this proof. The first is the completeness axiom of the real numbers. If S is a subset of the real line, it's bounded above, then S has a supremum. That is a least upper bound. And the definition of continuity, we're going to use epsilon delta continuity in this proof. So F is going to be epsilon delta continuous at x naught. That means for every epsilon, there exists a delta, such that for everything in the domain, if this distance between x and x naught is less than delta, then the difference between f of x and f of x naught is less than epsilon. So you'll notice here that I didn't represent the function here. I didn't want to bias our thinking by saying, okay, it definitely goes through. And I couldn't draw it so that it didn't. And so I just want to pretend here that the function value here is kind of known, and here is known. And here it's an utter mystery. The function must be doing something, and it must be a continuous function, but we don't really know what to expect of that. I did, however, draw a region of values here nearby f of a, where the values are definitely less than y. And here I drew a small region around b where the values are less than y, greater than y. And I want to emphasize this fact that if the value is less than y at some point, then it will be less than y on some window around that point. And if it's greater than y at some point, then it will continue to be greater than y on some window around that point. Now that's not quite the statement that we need, but we're going to begin with that, and we're going to see how we can use that to prove that there must be a value in between. So first we're going to prove this slightly negative result. So let me claim this negative result here. So if f of x naught is less than y, then there is a region x naught minus delta, x naught plus delta, so a little window around x naught. So x naught might be here, and we have a value which is less than y, and what we're saying here is there is some region on which the function is still going to be less than y, so on which f of x is less than y. Basically, if you have a negative result at one point, then you will have a negative result on a whole neighborhood at that point. So it's not quite clear how this claim is related to this statement, but let's prove that first. So this is actually nothing more than a simple application of continuity. So let's prove this claim. So if f of x naught is less than y, then choose delta to be y minus f of x naught. Sorry, that's not delta. Choose epsilon to be that in the definition of continuity. And then, having that epsilon in mind, we choose a delta for epsilon. So notice, first of all, that continuity allows a statement for every epsilon greater than 0. And if indeed f of x naught is less than y, then y minus f of x naught, the gap between here, is definitely a positive value because f of x naught is less than y. So that's positive here. Then we're going to choose delta for epsilon. And then what does it mean to get that delta for that epsilon? It means for any x in the domain of f, if x minus x naught is less than delta, then f of x minus f of x naught absolute is less than epsilon. Now let's unpack this in terms of what this means. This means that x is between x naught minus delta and x naught plus delta. And this means that f of x is between f of x naught minus epsilon and f of x naught plus epsilon. But what is f of x naught plus epsilon? If we take this, we've chosen epsilon to be y minus f of x naught, right? So if you take this f of x naught and add it to both sides, f of x naught plus epsilon is y. So that's y. So now let's read this and see what it tells us. It tells us that whenever x is between x naught minus delta and x naught plus delta, then, among other things, f of x is less than y. So this demonstrates that if we have a value x naught for which the value of the function is too small, f of x naught is less than y, then we will have a small region around that x naught, some delta to the left and delta to the right, where the value of the function is similarly, still going to be less than y. Now, the opposite is going to be true, and we might as well state it here. And let me just illustrate that that is equally true. So if f of x naught is greater than y, then there is a region, and it's the same region. So there is a region x naught minus delta, x naught plus delta, on which f of x is greater than y. So basically, if we have a point up here where the value of the function is too large, f of x is greater than y, f of x naught is greater than y, then there will be, so that's a value x naught here, it's too high, then there will be a little delta neighborhood of x naught on which the value remains too high. Let's prove this next. It's basically the same proof, but I want to be careful about this. So we're going to choose epsilon to be, in this case, f of x naught minus y. So kind of the opposite of this. We're going to choose epsilon to be this distance here. So f of x naught minus y, maybe we'll represent that in red. So this distance here is this, that's epsilon. And we're going to choose delta greater than 0 for epsilon in the continuity of f. So using this definition. And then what do we get? We get for all x in the domain of f, if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon. And let's unpack what this means. It means if x is between x naught minus delta and x naught plus delta, then f of x, I may need more room, then f of x is between f of x naught plus epsilon and f of x naught minus epsilon. But notice that f of x naught minus epsilon was exactly what we chose to be epsilon. No, I'm sorry, I said that wrong. f of x naught minus epsilon can be deduced from this equation. We add y to both sides, and we subtract epsilon from both sides, and we see that f of x naught minus epsilon is equal to y. So basically taking this height f of x naught and subtracting epsilon brings us back to this height of y. And so among other things, this tells us that if x is in this region, x naught minus delta, x naught plus delta, then what do we get? We get this. F of x exceeds y. So that means that on some region, f of x naught, on some region, x naught minus delta, x naught plus delta, surrounding this problematic x naught, then we have more problems. We have the function is going to be too large on that entire small interval. Now, this might seem very fatalistic. It might in fact seem like we're unproving or anti-proving the statement that we're saying this can't happen, because what I've really demonstrated here is that if the function is too small at one point, it will be too small in a neighborhood of that point. And if it's too large at a point, then it will be too large on a neighborhood of that point. And it might seem like we're proving that it cannot possibly pass through x because it will always be too large or too small. Of course, that's not really the case. We know that it can pass through here, but nevertheless, these claims are true, right? If you are too small, then there is a neighborhood on which you're too small. If you're too large, then there's a neighborhood on which you're too large. The point here is that we do expect there to be a point here that is just right. We need to identify how to find that point. And we're going to use these claims. These claims are going to be instrumental in demonstrating that we have such a point. All right, so now I'm going to erase these claims because we've proven them, but I want you to keep them in mind, and we're going to try to identify the point x. Now, x. Now, the challenging thing about, I think the challenging thing about the proof of the intermediate value theorem is that there's no particular obvious strategy by which you should try to identify the point x, right? We don't know anything about the function. It's not like we can solve equations to find the value of x. It's an arbitrary continuous function. There's no obvious strategy for identifying the point where it crosses through. And we might say, oh, well, we'll cut this in half and cut this in half. But then, is that process bound to finish? I mean, such a strategy could work, but it's complicated, and it's not clear what strategy we should use to find the point x. And so if we want to use completeness directly, then we do have some strategy that will work. What we can do is we can calculate all of the x values for which the function f of x is too small. And then we can try to find the edge of that set. We can try to find the boundary or threshold between the place where it transitions from too small to too large. And so what we're going to do is, instead of focusing on this condition, f of x is supposed to be equal to y, we're going to focus instead on the condition f of x is going to be less than or equal to y. In fact, we're going to focus on less than. F of x is going to be strictly less than y. And then we're going to try to identify the threshold between that set and its complement, so that we can find the x which is right in between. So let me define the set that we're going to reason about. So we're going to let S be the set of all x's in the interval so that f of x is less than y. Now at this point, it doesn't really matter whether I say less than or equal to. Both ways will work, but it's a slight difference in the proof. So here S is going to be this set. Okay. What do we know about this set? So let's graph it first. What we're doing here is we're identifying all the x values for which the function is less. Now, you might think that this is going to be like the left half of this will be s, and then the right half will be the complement, but not necessarily. This could have this doesn't even have to be a connected set, right? Because these are the values for which the y value of the function is going to be less than y. And the function could, in principle, go back and forth across here. And so we could get a disconnected set for this s. So I don't know what s will look like, but it will be some set. And I do know that the set will include A, so S is not empty. So notice A is in S. I know that A is in S because f of A is by presumption less than Y. So I have at least one thing in here, and I could use one of those claims to say that I have a region of things in there as well. So here I have this set. Now, what will we do with this set? We want to explore it's not actually the set that we're interested in, but the threshold where the set meets its complement, the boundary of that set. That's what we're really interested in. We want to identify the points that are in the boundary of this set, but we only need one, and the easiest way to find one point in the boundary of this set is to take its supremum, because the supremum of that set is the highest. It's the maximum value of that set if the maximum exists. And if the maximum doesn't exist, then it's the upper threshold of that set. And so the supremum is really what we're after here. So let's identify the supremum, and I want to give it a symbolic name here. I can't use S, and I don't want to use X. Yeah, okay, let's call it x naught, actually. Yeah. So let's let x naught be equal to the supremum of S. Okay, so somewhere along here, we have some supremum of this set, which we're going to call x naught. Now, we suspect that f of x naught is going to be equal to y, but it might not be, and so let's not take that for granted. But let's claim it so that we know where we're going with this. So we'll prove that f of x naught is equal to y. Now, before we prove that, I want to prove that x naught is a funny kind of point. Points slightly to the left of x naught will be in the set S, and therefore they will have values too small. And points slightly to the right of x naught will not be in S, and so they will have values too large. So let's prove that x naught is really it's a dividing point. It's a dividing point. Before we prove what f of x naught is is going to be a dividing point, so that values to the left of x naught, we will be able to find some values to the left of x naught for which f of x is too small. And we will be able to find some values to the right of x naught for which f of x naught is too large, or just right, which is just as good. Let's prove that next. So let's actually claim that next. So claim. So for any delta positive, there are, well, let me simply say, there exists x in the region from x naught minus delta to x naught, so that f of x is less than y. Okay, so basically what I'm saying here is, if you look even slightly to the left of x naught, then you will find, well, some orange points in there, right? You will find some x values, some x, and f of x will be too small. And that's because x naught is going to be the supremum of S. So let's prove this next. So the secret here is that x naught minus delta is not an upper bound of S. Notice that x naught was the supremum of S. And if I subtract a little bit, then that's not an upper bound of S. So there is some x in S so that x exceeds x naught minus delta. So this is basically just what it means to not be a supremum. Sorry, not be an upper bound. X naught is the supremum. Anything less, like x x naught minus delta, for example, is not an upper bound because it's less than the lowest upper bound. And if it's not an upper bound for the set S, then there's an element of the S that exceeds that value. And then what does it mean that x is in S? So then f of x is less than y because it's in S, right? Because x is in S. I should have, so let me point out here, I don't actually know at this point whether the x, which is in S and greater than x naught minus delta, it could be equal to x naught, I guess, but it couldn't be any greater than x naught. So I want to point out here that x is less than or equal to x naught because it's in S, and because x naught is an upper bound for S, right? If it's an upper bound for S, then it must be greater than or equal to every element of S, and x was an element of S. So actually, I know that x is going to be somewhere greater than x naught minus delta and less than or equal to x naught. So this should have been that kind of bracket there. So I'm revising my claim slightly. That gives us the claim, right? For any delta, you subtract a little bit. There is an x in this region with f of x less than y. And now I want to claim the opposite. I want to claim that for any delta, if you look up here, then there's going to be an x in this region whose value is going to be greater than or equal to y. So remember, x naught is the upper limit of this set S, which has all the places where f of x is going to be less than or equal to y. If I exceed that value, then we'll get greater than or equal to y. So let's state that next. So and this is going to be much easier to prove. So for any delta positive, there exists an x in the region x naught to x naught plus delta, so that f of x is greater than or equal to y. And this is actually much easier because that's going to be true for any x in that region. So maybe, so just notice here that, so if x is, so if x is any value greater than x naught, then x is just not in S because x naught is an upper bound for S. So then it's not going to be in S. And if it's not in S, then f of x is going to be greater than or equal to y because the definition of S is that it's all of this x's for which f of x is less than y. So we get x values greater than or equal to y on the right, and we get x values, we get some x values anyway, less than or equal to y, f of x less than or equal to y on the left. So x naught is kind of special, but not yet special enough. It's special in the sense that if you look any tiny distance rightward, then you get f of x values that exceed the target value. And if you look any distance leftward, you can find anyway some x values for which f of x is less than the target value. This seems to be zeroing in on the problem, but it doesn't seem to solve the problem. It seems like we've just shrunk the original situation into a smaller version of the same problem, right? We still need to get this connection between them. But in fact, we're virtually done because of the first two claims. So let's think about what the first two claims said. The first two claims said, if any value f of x naught is less than the target value y, then there is a neighborhood of that x naught on which that is equally true. And if the same value x naught has f of x naught greater than y, then there is a neighborhood on which that is also true. This x naught, supremum of S, has values on the left which are less than y and values on the right which are greater than y. And that's true for every delta. No matter which delta you pick, you can find some value a little bit on the left so that f of x is less than y, and some value a little on the right such that f of x is greater than y. And that means that it cannot satisfy the conclusions of either of those first two claims, right? It cannot be a point at which every neighborhood, every delta neighborhood has, you know, it cannot be, I misspoke, it cannot be a point for which there is a delta neighborhood such that the function is uniformly less than y. And it cannot be a point for which there is a delta neighborhood for which every value of the function is greater than y. And so it cannot satisfy either of those claims. But what are the hypotheses of those claims? The first claim says if f of x naught is less than y. The other claim says if f of x naught is greater than y. It cannot be described by either of those claims. So, what do we conclude? So by the first two claims, so neither case f of x naught is less than y, nor f of x naught is greater than y is possible. So I want to go over this one more time because this is confusing. So what were you, not these two claims, but the ones I erased. By the first two claims, the first says if f of x naught were going to be less than y, then we would have a delta neighborhood for which it is uniformly less than y. But then that would contradict this property here, that to the right of it, we get values greater than or equal to y. If this were true, then by that other claim, now erased, then we would have a neighborhood of x naught for which we always get values greater than y. But then that would contradict this, right? That there is, on every delta neighborhood, we get some values less than y. And so neither of these things is possible in the context of what we've proven here. Well, there's only one other option, right? It's either less or it's greater or it's equal. And if we've ruled out less and ruled out greater, then it must be equal. F of x naught is equal to y. And so we have finally shown here that that must be the point at which the function, or at least one of the points at which the function crosses through that critical value there. And this completes the proof of the intermediate value theorem.